I think we're recording. Okay. So welcome to the seventh lecture on this generative modeling using VAs. So we'll do a quick recap of whatever we have done till now, so that because we'll do today the PyTorch simple code on VA. How do we code up, and how do we look at the gradients? How do we code up the loss function especially, and all of that, right? And what are some things that you need to keep in mind when working with implementing as such. So theory wise, I guess we have done a lot of stuff, but implementation sometimes has their own challenges and issues. So you need to think about what else we need to add to make sure that we are able to operationalize it better and get good results out of it. Again, so we'll just start with the modeling idea. So our main idea or our main question is basically a generative modeling problem statement where we have some samples from an unknown distribution, and we want to generate samples which are more like this particular sample. Now, the like as such can be defined in many different ways, and will not consider that right now. The idea being that this is again a different problem in itself. So we looked at this idea of variational inference, where we first intuited the idea of latent spaces as such. Again, coming from the idea of manifold hypothesis, where we said that there is something lower dimensional representation possible for every big data set that we have out there. And then we use variational inference to be able to approximate that particular latent space, right? And then we looked at the formulation in detail. We started with this idea of um, just a moment. Yeah. Okay. Um, yeah. So we start with the idea of this. So how do we use this variational distribution in VAs? And we came to something called as a lower bound on the log likelihood of the data. And we then said that okay, so if we maximize the lower bound, it's like maximizing the log likelihood. And we also obtain what is the level, like how tight is the lower bound, and we also got a good nice expression for that, right? And then we looked at this elbow, this lower bound in more detail, and we came out seeing that it looks like something like your autoencoder sort of a formulation, where you're trying to map this data point that you have to some different space, and then trying to reconstruct that same data point from that space, right? Although this is a bit, using a probabilistic distribution rather than a deterministic transformation on that data point X. Uh, and we also got a KL difference between the approximate latent posterior and the model prior. And we then saw the various assumptions that VAE authors have made to make sure that we can operationalize this particular sort of a formulation. And then we also spoke about the DKL term in the elbow in more detail, because we had two Gaussian distributions. So we came out to be so we got a good nice expression which was closed form in this in the parameters and in the data that we have at hand, which we're evaluating. And then we spoke about reparameterization trick, and why would we need something like this in the first place? Because we want to take the gradients with respect to the with respect to the decoder and the encoder parameters of this particular term, right? And because the distribution itself depends on the encoder, when you sample from it, you need to be able to pass the gradients. And the issue here is that the sample as a function itself is not differentiable. We then used this transformation theorem for Gaussian distributions to be able to separate out the um, randomness part, and the deterministic part, and so we could take a gradient with respect to these parameters. So this basically came out to give us a way to solve for this a way to solve the VAE algorithm for a single data point. We then looked at multiple data points. That is, for example, if you have like a set of data points which is given to us, so then how do we use this idea? From very simple comparisons, we saw that we can just maximize the expected elbow over this whole data set, and that gave us a way to operationalize the VAE using using a batch of data or using a batch of data points that we have, samples that we have. And we also spoke about this gradient descent, how we can apply. We just make the loss to be the negative of the this elbow that we have at hand. And then we also saw how do we finally sample from it, and how do we infer, how do we do inference through this particular VA. We saw that for samplings for generating samples, we have we'll use a decoder, and for inference we'll use the encoder part of the network, right? And we also saw some issues with this particular thing in the last class. So we spoke something called beta VA. So we brought the intuition using this idea of Lagrangian optimization, and then we said, if you want to make sure that our latents are more sort of independent with among themselves, we can use a parameter called beta to enforce that to happen, right? And we also found that this basically has some sort of a Lagrangian sort of a approach to solving this optimization problem. We then came to the idea of info VA, where we showed that it is possible for the normal VA loss to be optimized such that we don't have the latent learn anything about the data, and that would cause problems in inference issues. So hence we explicitly gave a additional constraint to the model to be able to maximize even the mutual information between the latents and the data. And we saw how that came out to be, and we have this DKL between the posterior aggregate posterior and the latent prior till now pending. How to solve this? We'll take it up in the coming classes. We then saw something called the VAE with VAM prior. So where we said we challenged the assumption of why should your P of Z should be something like a Gaussian distribution. So we asked the question, what is the best prior that could be there? We found that to be, again, not surprising, that it's basically the mixture of the gauges that we have at hand, which is the posteriors. And we saw that this can actually lead to computational issues and also overfitting, because whatever would happen, we will have to use only from the data that we have at hand. We would get samples from this. So rather, we said that, okay, we'll use something called pseudo inputs which will learn what which will be kept learnable, so as to provide some sort of a trade-off between completely overfitting, that is when I use all of these data points, versus the on the flip side, where we had only Gaussian distribution being used, right? We then spoke about VQVAs. VQVAs tackle another big assumption, that why should the latents be a continuous random variable? Again, so it's more the fact that so VAs or basically variational inference methods, they don't have any constraint that latents should be continuous random variables. It is just that this was the way that was happening for a while, especially in the image data space. So they used something called as vector quantization system to be able to build this VAE, from scratch. So we then saw how different issues that we tackled in the usual VAs came about here also, and basically how to solve them. So the issue of, for example, how to pass gradients, the issue of how would you do inference, and so on and so forth. right? And we also saw, because we have these new vector quantized systems coming in, how do we train those particular parts of the network also using this something called as top gradient parameters and approaches and so on. And we also saw about how to do sampling, because one very critical part of VAE was the fact that the posterior distribution was in fact a probability distribution. So if you actually sample different values, you will get different outputs from your decoder. But then here, since everything was deterministic, how do we do a sampling? So we said that, okay, we'll actually have to do some sort of additional sort of a probabilistic model, which will look at all possible encoder outputs and give you new outputs which can be fed into the decoder to get new samples. Post this, we looked at a very general sort of a problem statement called the conditional generation. We again spoke about where this could be something useful. And we also saw this idea of conditional VAE, basically. So where your latent dimension now depends not only on the data, but also on the label that is being passed, right? And then we saw how the elbow turns out to be, how the architecture should ideally be, and so on. And we spoke about some use cases where this is being used and can be used in general, right? So that we also gave a starting idea about this something called as adversarial learning. So we'll consider this either today or in the next class. Okay, so with this we'll start the PyTorch tutorial. Again, I've shared the the what do you call that? The PyTorch notebook. So we'll go to that the Colab notebook there and see what all can be. We'll try to intuit what we have seen, what we have learned till now, how we can build upon making it a operational system in some sense.
Right.
Yeah.
So how should we go about it? Shall I open it? It's already open and I have run so installation is already done.
Okay.
And the model has also been trained.
Okay, good. So we'll do one thing. We'll go through the code line by line. I mean, most of the part which I want to explain, and you can also ask if there's something that is unclear or
Okay, fine.
requires you to understand anything more. We can do that.
Yeah.
Cool.
And is there any particular reason for using PyTorch or compared to either Keras or TensorFlow?
No.
Or just for convenience?
Yeah, it's just based on my convenience that because I've been on PyTorch for a while, so I'm used to the PyTorch way of writing code and stuff. But yes, so there is no reason why you cannot use Keras or TensorFlow as such. Again, all of these libraries are almost they work they work like head to head in terms of support for features and everything. So I guess any of the libraries are fine. Yeah.
Okay.
Okay. So yeah. So we'll use these particular combinations of these particular libraries right now. So just to make sure that things are reproducible everywhere. So whatever sort of going forward, also if somebody wants to use the same code and get same results, they can get that by using this exact version of libraries that we have shown here. So that's the
just one question.
Yeah.
When we install something in this, I will ask some general questions also because I'm not even aware of those.
Sure.
So when we install something in Google Colab, does it stay on for some time or does it get see, for example, we are installing some libraries right now. So will it stay even after I close this window?
So there's something called a runtime here. So basically, so we're currently in this particular runtime right now. So if the runtime closes for whatever reason, for example, say it's possible that your RAM short up very badly and close the runtime. So then whatever you have installed will go away. So you'll have to restart the whole process.
Okay, so it's very limited.
Sorry.
Then. So it's very limited then, like.
Correct. Yes. Yes.
Okay. Okay.
Until it is running or basically it's not stopped in for whatever reason
Hmm.
it'll be there. But once it is gone, it's gone. That's the idea.
Right. Right. Hmm.
Yeah. So yeah. These are different libraries just to make sure that things are working hand in hand with all
Hmm.
the different libraries here. Uh, and we'll also use something called as PyTorch Lightning. Now the issue or basically the difficulty in using PyTorch comes basically because a lot of code that you have to do the training code and the testing code, etc. You have to write by hand. So there's nothing like where you say you have a model, have a data set, just run this model on this data set. So you have to write that exact batch level sort of code. So PyTorch Lightning sort of gives you like a packaged version of that PyTorch that you can use. So we'll use it to make sure our lives are a bit easier to run this code, because the aim of this tutorial right now is not to teach PyTorch as such, but rather to see how whatever we have learned till now through our theory, how does that come about in a mostly a coded sort of a model, right? And to see how things may or may not work for that matter, right? Again, there's a bunch of imports. We'll see how each of them is being used in going forward. Again, so then coming to the idea of VAE, we said that we have a encoder and we have a decoder. So the encoder ideally is supposed to give me two parts of the output, output. One is the mean of the latent and the variance of the latent, right? And we also said that the variance matrix that we have, the variance covariance matrix, will be a diagonal matrix. So at the end, what I need is I need basically uh, two sets of values, one of which has the mean values of each of those latent dimensions, and the second set of values which have the variance of each of these it at n dimensions, right? And what we'll do is we'll use the famous MNIST data set. So again, so MNIST data set, if you want to think about, so the idea is that we have all of these sort of images, grayscale images of different writings. For example, it says so all these 0 to 9. So the idea is that so each of them, so for each of them we have what the image was and what the symbol the digit was ideally, right? For example, now all of these are zeros, all of these are ones, and so on. So the data set as such, which you will be using, has both the entries. It has the image as well as the label with it, right? But what we what we'll be doing right now, it's just using the images, trying to generate more images which look like these digits in hand, right? For example, so using these for example images, can we generate a new 5 which is not there in this list of fives, right? That's the idea. And then so each image here is a 28 cross 28 image having one channel that is just a grayscale channel. So what we'll do is we'll flatten out that image into a single vector, so that becomes a 784 dimensional vector. And we have some layers through which we are passing this particular vector through. We finally have two outputs from this particular model. One is the mean and the log of the variance, right? So we also spoke about this idea that because we want because variance as a quantity itself is a positive value, so trying to predict the log of the variance would be a better thing, because we then don't have to deal with like the positive part of it and all of that. Rather we just we'll break the log of the variance and then raise to the power e to get the actual variance values that we have that we want, right? So this is the model definition that we have. We're going to uh, initialize each of these particular layers using this gaming normal, and 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 then we define how should the data proceed through this particular model, right? So for example, let's say, so the forward function basically takes in all the arguments that you require for the particular model, right? For example, let's say, so here we just have the image, right? So we have the image. I'm basically reshaping it from a 28 cross 28 sort of a matrix into a 784 cross 784 dimensional vector. So that that's happening here, right? And then I'll pass through the first layer, put an activation through it. We're using the activation function of elu, and then we have second layer again passing through an activation, and then whatever output I get, the output I pass through both the mean predicting part of the encoder and the log variance predicting part of the encoder, that is mean and log var. Now, it's possible that sometimes, because of whatever architectural choices or your, let's say, bad luck or whatever, so it's possible that this log variance that you get can go up to, like, for example, higher than what the floating point representation allows in a particular model. So so we see these sort of issues in basically implementing what we have seen in theory. So it's possible that sometimes issues like floating point occurrences which can lead to nans in your output can occur. So one general trick that people use is they basically clamp the log variance between some sort of minimum and maximum. The clamp function is again differentiable. So we use that to be able to make sure that we don't blow up or go below some very possible values for the log variance. So just for us to make sure that we don't go across the floating point representation allowed values, right? So this is the encoder module, right?
So okay, fine.
Yeah.
And this K email is basically like just assigning some random which to start off with
Yes, correct,
in a
yes.
normal fashion.
In a normal fashion, yes. So this particular theory basically comes from, like, what is the right way to initialize any layer in a neural network. So based upon what the activation is, your the way you initialize your network can change. So for ELU, um, uh, there is there can be something better, but what has been used currently is that gaming normal works fine for ELU based activation functions.
Okay, sounds good.
Yeah. Okay. So yeah, so that's the part of the activation function. Just a moment. Yeah. We then have the decoder basically. So again, remember what the decoder is supposed to do. So basically, decoder takes in one sample of your latent, right? And then is supposed to generate the image at the end, right? So basically, so we have the latent dimension here. So we have the using three-layer network. So where we go from latent dimension to, let's say, some dimensions here. Finally, we have like a 784 dimensional vector output from this particular layer, let's say layer 3. And the way we go through the model is basically we have a latent, let's say x in this case. So we have we pass it through the different layers and their activations. We also use a different output activation here. So again, the idea here is that because the output image that we have is a grayscale image, the values will always be between 0 to 1, right? So we can either use sigmoid or hard sigmoid. So hard sigmoid is basically linear in some part of the space, and then it basically becomes flattened at 0 and flattened at 1 also. So something like this, right? So the bigger idea between sigmoid and hard sigmoid, the issue is in sigmoid you can never reach the value 0 or never reach the value 1, whereas here the idea is that post this particular, let's say 3 here, you you can realize the value of 1 and you can realize the value of 0 also, right? So hence I chose let's say hard sigmoid as the activation, but again feel free to try sigmoid activations and see how the output changes, right? Uh, uh, and so but at the end, the idea is that the layer 3 what we have here gives one vector. Basically it gives you one vector of this 784 dimensions. So we need to reshape it to basically make an image, which is again done through this particular operation, right? So we have so how many samples you have, that comma 1 comma 20 cross 28, that is, so these two are the height and width of the image that we know for a fact, and one is the number of channels, which is it's great, it's grayscale image, so we just have one channel in this particular image data set. So this is the encoder and decoder. But the more interesting part of the idea, as we know, is basically how to connect these 2 points together, right? Using sampling and using different ideas that we have already seen. So first thing what we do is we make sure that we initialize the model well. That is basically make the encoder and make the decoder as part of this particular model, and we basically initialize both the encoder and decoder. So all of that part is done. So here is the idea, this seed everything of 0. So it's a function from this PyTorch Lightning library. So where it makes sure that it seeds the NumPy library, the Python random library, and so on. So because all of these libraries have support for randomness in them, so it's better to make sure that we seed all of them together, so as to make sure that if I run the same code, let's say 3 days later, also I still get the same results, right? So these are some things that we need to take care when we are actually trying to operationalize a lot of these ML models in some sense, right? So we'll now look at how to run this VAE model. So first thing is very clear. So we get the so we run the data that we have, that let's say X, for example. We run that through the encoder, and we get two outputs from the encoder. So mean and the log variance. And then as we spoke, right? So in the original paper also, the authors say that we can use one sample from the latent space, right? So what we'll do is we'll get one sample for each of the uh, values for each of the samples that we have in place, right? So for example, something like this, right? So we have so we'll use toss.normal 0 1, right? So because 0 mean and 1 is the variance here, and we'll get one value per sample in this particular batch of values, that is X. So that becomes the epsilon, right? The randomness part of it. Now we're constructing the variance, so the latent, using this sort of formula, which is the mean plus half times the uh, exponent of the log variance times the epsilon, right? So if you basically see here, so toss or exponential of log variance gives you variance, right? And then we're doing this half with it. This doesn't make sense. Mm. It should just be sigma times. Oh, okay. The half has to be inside the in a log variance. But again, so some basically
Yeah, that is fine.
sorry.
That is fine. I understood. So just the conversion that we studied, like
Please.
latent equals to
Right.
normal plus mean and multiplied by variance.
Right. Right. So
Yeah.
okay. So we get the latent in this way, and we then pass the latent to the decoder to get one value, that is x hat, that is the constructed output, right? And we then pass all of these values outside of from this particular model so as to be used in computing the loss and stuff. So now we'll look at the loss calculation. So again, so the the idea is we get, let's say, one batch of values from the data set that we have. So the batch basically has the image and the label. So we currently how does the label in any sense? So we'll just ignore it. So we just have the image that we have. So we will do the this float conversion just to make sure everything is on par. So then we pass this. So this self of x basically in a PyTorch model or a PyTorch Lightning model basically passes through this forward function, right? So self of x means it's like calling self dot forward of x, right? So basically I'll pass this x through this forward function. So which means I have the mean vector, the log vector, and the x hat vector for each of the sample in x, right? We then do the MSE loss for this one. So we discussed why MSE loss could be a good reason, because we are assuming the decoder output to be a Gaussian distribution again. So maximizing that log likelihood is equal to minimizing the MSE loss over the output and the input vectors, right? So how do we do that? Basically is that we say, okay, find the MSE loss for each of the dimensions, right? So we'll say the input is, let's say, x hat, and the target is x, right? We then take the sum over all the dimensions, right? Because we want to do x minus x hat L2 norm, right? So we'll do that and then do half on the outside and take the mean over all the possible samples, right? So again, remember, the mean has to be taken across all samples, not across all dimensions, right? So we add up all the values across dimensions, right? So because 1, 2, 3, then that's the dimension of the data set that we have. That is 1 cross 28 cross 28, and then we take the mean across all the samples, right? So this is the reconstruction loss. Then we have the KL loss. So if you remember the KL loss, we had a closed form expression here. So that is basically this expression. So if you see, we have actually, let me just pull up the this one. So this won't work. One second. To share the screen completely. Yeah. Yeah. Okay. I hope you can see the OneNote also now.
Yeah, I can see.
Yeah. So we have this idea, right? So where we have the DKL term coming out to be like this, right? Where we said that this becomes uh, minus half of product of all the variances, right? Now because we have this to be we are predicting the log variance. So this can be seen as just the summation over all the dimensions of the log variance, right? And then I can just look at it as e power. I can do this. right? So I get something, this term would be solved in that way. Then I have the mean across all the, the summation of all the mean squared, right? The mean vector. Uh, and then individually, all the variances also have to be added. So I need to do the exponential first and then take the summation, right? So all of that is basically happening here. So as you can see, I have the mean squared. Then I have the torch dot exponential, that is basically this part of the code, right?
Hmm. Yeah.
This part of the thing. And then I have log variance. That is basically because I can just take the summation of the variances here. And then this minus one, I guess, comes by this d by 2. No, no, this log minus 1 will come out to be solving for this. And then I take the sum across dimension equal to 1, because I want to do across all these dimensions. So the summation needs to be done across all these dimensions, right? So,
Number of samples. Number of
the
latent.
latent dimensions, yeah. So
Yeah.
I 1 to r, right? And then we need to take the mean over all the samples. So this
Hmm.
summation equal to 1 gives you that there's a summation across all the latent dimensions, and then this dot mean is basically the mean across all samples,
Hmm. Right.
right? So then finally, our overall loss comes out to be the reconstruction loss and the KL loss. So as you can see, we are trying to minimize the reconstruction loss, right? Which means maximizing the that expected log likelihood, right? This particular term that we had, and then when we worked out this KL values. So we want to minimize the KL divergence also, which is exactly this term. So we have plus KL loss coming up here, right? And this is a simple check in case anything becomes nan, so that we can
Hmm.
figure out if
Yeah.
something is going wrong or what. And and we then log all the losses. So basically, we want to look at the overall loss. We also want to see how different losses, components of the loss are working, the
Okay.
reconstruction loss
So
and the
reconstruction loss, scale loss. Yeah.
KL loss, right? So this is basically the part that the whole crux of the matter, right? So basically, so 2 points. One is this, right? So we are doing the sampling part, and z becomes a differentiable quantity because of this reparameterization trick, and the common step. So where we get the reconstruction loss and the KL loss, right? And then we just have these usual thing like, okay, so what should the training step do, the testing step do, and so on. So again, the idea being that both of them are very simple, very similar, so we can just common out these functions and write this common step sort of function, right? And then we have we want an optimizer, which is we're using Adam optimizer, again very standard sort of approach, choice here. Uh, and and then we can also give what should be the train and the test data loaders, right? So this is the power of PyTorch Lightning as such, because now all of this is in one place. So anything you want to change, you can just come change here and move ahead. So we're going to use MNIST data set, which so this train equal to true tells you, okay, which part of the MNIST data set should you use for training. So we say, okay, so give me the training part, and this is the testing part, train equal to false, and we say download equal to true, because in case it is not already present on the hard disk, please download it so that you can use it from the hard disk itself. And we also perform some basic transformations. Again, this is just coming from the ML, iteration, because to make sure that your data has mean zero and sort of uniform variance. So it'll help in better convergence of your algorithm. So we make sure that the train and the test both have the similar transformations applied to them. So what it does is it basically gives you a scaled version from 0 to 1, and then we say that, okay, subtract half from this, so that now I'll have the data between minus half to half, right? That's the thing that is being done in the train and test data loader. So we'll now see how the how the model looks basically. So the summary function as such, that helps us understand what the different input shapes, output shapes are, and this also helps in trying to debug any issues in terms of matrix multiplications. For example, was there any thing that you thought would be some shape but didn't turn out to be, and so on. So what we'll do is we'll just make a model, make a model here like this, and say try to run a sample of 10 samples of 1 cross 20 cross 28 through this particular model, right? And show me what all different layers exist, what do they do, and so on. So if you see here, very neatly it has given us. So first is the encoder and the decoder, two parts of it. Encoder has again two layers and two activations, the ELU activation that we have, LU activation, and then we have two another linear layers which we have named them mean and the log variance. And as you can see, the encoder basically takes in let's say 10 images of the shape 1 cross 20 cross 28, right? The linear layer acts upon this 784 dimensional vector, gives me 56. The ELU doesn't do anything to reduce the shape. It's just applying the function point wise. That is, for every element goes through this ELU activation function. We then have the layer 2, which does again the next sort of reduction, and then we have finally the linear layer, which takes in 28 dimensional vectors and give you, let's say, 10 dimensions output. That output was given by this latent dimension, right? So we're saying that encode my data in a 10 dimensional space. So that is this 10 dimensional output, right? And we can see the parameters here basically. So again, if you multiply this 784 with 56 and take the bias terms also, you will get so many parameters are being learned as part of each of these layers, right? So that's the encoder layer. The decoder layer, as you can see, again takes in a 10-dimensional vector, the latent vector, and spits out finally a 784 dimensional vector, which is then reshaped into 1 cross 20 cross 28 image, right? So that is this idea. So we basically have so many parameters and all of that is being shown here, right? So this basically is the model definition. So any doubts till now? Anything unclear also you can ask. Any choice here and so on.
So I think it's clearer.
Okay. Okay, good enough.
Like quite straightforward.
Yeah, exactly, right. Yeah, correct. So then we'll now move on to how do we train this something like a this model. So we'll again use seed everything of 0 just to make sure that all the randomness is controlled for, and so that we can basically make sure to reproduce this data, these results whenever we want to. So we'll make the model now. We'll say okay, use 10-dimensional latent and 256 as your batch size. So we then use something called trainer. This trainer is again comes from the PyTorch Lightning library, which tells you how many max epochs you can run through, logger, and so on and so forth. Many different ideas, but the bigger point is how many epochs you want to run through your data. And then you can say fit the model, basically, that is use the training data set to fit the model and test the model on your testing set. And you've already defined what the trained data set should be and what the testing data set should be, right? As part of the model itself. So we then do that, and you can see like these different iterations of running through your the training and testing and all of that. So finally, the bigger point is you can see how the reconstruction loss, the KL loss, and the final loss, etc., are changing through different epochs, and we can also see what the metric on the test data set is, right? So basically, so post training, so if you see here, so we have the test metric that is basically on the test data set, what the KL loss was, what the final loss was, and what the reconstruction loss was, right? And any observation to make here, by the way? Uh, Anything that you feel is off or something worth noting in these three values?
So KL loss is very less, whereas like K test KL loss, okay, that is 1 point something. Test
Right,
loss, test reconstruction loss. Right, right.
right, है ना?
Reconstruction
So
loss is
is basically very large, right? So
right,
so
right,
what so generally what ends up happening is, I mean, and 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 can you think like why this could be like one
yeah,
very
yeah.
strict,
So
right?
because yeah, because KL divergence, the maximum value could be 1, whereas like reconstruction loss is like mean square error, which can take any value, any positive value. So like that's why these two numbers are like very different.
So as you said, mean square can take any value, but but k loss it not be bounded by one, no? K loss can be infinity also, right?
Oh, I see. Because we are summing over like yeah, yeah.
Right. Huh.
Okay.
And the usual definition of K loss also when we were discussing. So we said that something like this, right? So let's take an aside here itself. So we said, sorry. So KLPQ, right, is P log P by Q, right? Something like this. So, but so the point being that, let's say if there is any point where Q has a very low value compared to P, so it's possible that this can blow up to a very large value, right?
Right.
So it's possible that the log will again, so such large value that log also cannot tame it down. So it's possible
Hmm.
that your tail can become very, very large, right? And this is
Oh, so
the
KL divergence is not between 0 and 1.
no. KL actually not between 0 and 1. Yeah,
It's always greater than 0. That's all.
correct. It's always greater
Oh,
than or equal to 2. Correct.
okay. So this I was like
Yeah.
mistaken. Okay,
So
fine. Yeah.
right. So because there's an expectation over a function log p by q, and this log p by q as such can grow can grow
Right,
large
right.
in any
Correct.
sense. So the
Hmm.
expectation remains unbounded, at least on the top. Bottom it is
Hmm.
bounded, right?
Hmm.
Okay. So, but yeah, but the point is right that MSC loss is not bounded. So, and what's happening here, right? So, the way we were doing the MSC loss here was that we were adding up all the values across all the other dimensions,
Right.
right? And which is exactly what the math also tells us. So we're not doing anything wrong in that sense, but it's just that what ends up happening is that we get very large values for the reconstruction loss, and so it's possible that for initial runs of your data set, this part of the loss will actually dominate your gradient movement. But once
Hmm.
these things start becoming closer or something, then it'll try to match both of them, like trying to do reconstruction as well as trying to make sure that the KL loss is also reducing. But currently, like from a very raw perspective, you can see that it just makes sense to boil down on trying to make the reconstruction loss as low as possible, because that's the bigger chunk of the loss here. So
Yeah, yeah.
so it's possible that it'll do better for reconstruction, but the KL loss, which makes sure that your sampling would be better, that you might be failing if you stop your training at this point of time. That's the one sort of intuition, that you should train for longer times and so on and so forth, right? Okay, so yeah, so this is one idea on so 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 we have run through the VAE model as such. We used all the knowledge that we had on the math and the basic knowledge of ML to make sure that we are able to train a VAE model. So one again, we'll come to the bigger questions, the idea of sampling, right? So can we sample from this VAE or not? So how do we sample, right? So we already spoke about the idea of how do we sample from a decoder, is that we want to pass different latents, right, through this decoder. And then whatever the decoder generates, that will be the image that the VA is telling us that belongs to this particular, let's say the PX, the data distribution as such, right? So how do we do that, for example, right? So so let's say I want to generate 100 images from this particular VA that we have trained. So I'll sample 100 latent values, so from again this usual N0 or N01 distribution, and just pass all these latents through the decoder, right? So what the decoder will give me will be the X hat. So I'll have now 100 such X hats with me, right? This squeeze is just to make sure to help for the plotting function, but this is not exactly required as such. Okay, so but the idea being that this X hat is actually a, so if you see the X hat shape, hat dot shape. So if you see this, this will ideally be 100 images, right? So 100 samples of 28 cross 28 image, right? And then we can use this basic plotly library to generate the images, to show the images as such. Again, fairly straightforward code, but the idea being that we'll use something like a heat map sort of a thing, because it's not easy to show one-dimensional images in its plotly library for whatever reason. So we'll use this heat map idea to gray out zeros and give ones whites to the ones. So as you can see, so the model does do some basic sort of things. For example, let's say it's trying to give zeros here, it's trying to do 3 here in some sense. And if you squint your eye a little bit, you might find like an 8 or something, right? And so on. So, but again, very interesting thing to see is we also have some very random sort of images here, right? Which doesn't make sense. Like why should that be a number in the first place? We don't know, right? But again, so the idea being that we have just trained for, let's say, 10 epochs. So that could also be a problem. So I would encourage to train for more and more epochs and see how your different how this VA is giving us better and better images at the end of the training, right? And remember, we have used 10 dimensions for your latent. We could also try to increase these latent dimensions and see probably are we able to better fit the data that we have at hand in this. Yeah, go ahead, Sanchit.
Yeah. So, and what is the typical number of epochs that we need to like get some decent amount of the generation? Or that I understand that that will depend on the type of data and type of loss function we are using.
Right.
But like, is it around 50, 60s, 100s, like that?
Yeah, so typically again, because it's a very simple data set and stuff like that, so people, I mean, you can try for 100 maximum. That should be more than enough, I guess. Post that, it may start overfitting or something. But yes, if you have large, for example, let's say large data set, or you have large number of parameters in the first place, right? So here we have very simple, I mean, the number of parameters are what, 90,000 parameters.
Yeah.
If you go for like more number of parameters, then more number of epochs might be required to make sure all parameters are working the right way that they are supposed to, right? Right. So yeah. So this is the VA mod tutorial. Again, all of this seems very uh, simple because of the fact that we used math to understand what finally it should be. So we could code all of these very simply, very straightforward to code all of these things in PyTorch, right? So any doubts till now in the running or something, or any curiosities you can address?
No.
Okay.
Not right now. It's clear.
Right. Okay. Then we'll so some simple things that, that you can try is so one thing that we discussed, what KL divergence was trying to do was that trying to make the dimensions independent of each other, right? So any idea how you would check the visually, at least how you would check the independence of latent dimensions in such a model?
So
So
you are saying visually.
visually at least, huh? Because
Okay. So,
yeah, so doing it on like quantitatively, this beta VAE guys, they actually gives a metric
yeah.
called disentanglement metric. But yeah,
Hmm.
but which how would you try to see if something is changing or not?
So just change the values in one dimension and keep all other dimensions consistent and generate some numbers, generate
Right,
some images, and see in which dimension are these, in which feature are these images changing consequently.
right. Right, that's it. है ना? So very basic idea. So basically, we generated a Z in this format, right? We sample from this normal distribution. So what you can rather do is basically choose two dimensions and keep the other dimensions to be same, and basically just try a bunch of values in these two dimensions and see visually like how all these different what dimensions capturing what aspect of the data, right? So that's one idea. Then we can so you can also do additionally is like check epoch level changes for images. Now what we have done here is that post training we have sampled these these different Z's and try to see how what decoder is outputting. So rather what you can do is you can keep this Z sampled first, like fix it and see at every epoch end how are the images being generated, right? So then you can see, okay, like what the model is trying to learn, right? So basically how is the learning progressing, like trying to reconstruct or trying to become more and more independent and so on, right? So those are some things that you can do to make sure you are to make sure your model is learning well. And again, this will become rather important when we go into GANs, because there is no really a good way to understand whether GANs are training properly or not. We will again come to those issues when we discuss GANs in detail. We also discussed about KL divergence calculation. So again, as I said that we got lucky in that sense that because we had both we had like Gaussian distributions, so we could get a closed form solution. So if not, what we'll have to do is basically take a Monte Carlo approach to getting these KL divergences, right? So we already discussed this idea here, right? So where we said that, just a moment. So we said that, so if you want to do KL of this one, KL of P Q, so we will have to look at, we will have to evaluate this particular expression, right? So what we'll do, we'll basically sample again different Z's from this distribution, and then look evaluate that value at P of ZL, right, which is your usual Gaussian distribution, and Q5 of ZL given X, you will sample from here, and its value also you will know, and then basically take a log of these two, log of the ratio, and that will be your KL divergence. So what will end up happening is the same way you were, so you had this Z equal to mean plus this one, right? So at the end, what you will do, you have a similar sort of code here, right? Instead of KL loss being sampled being calculated like this, you'll have sample Z. Again, you'll have to sample Z again using the same reparameterization trick, because the idea being that we want to be able to pass through the gradients, right? So you'll sample Z again, right, from these from using reparameterization trick, right? Reparam trick, right? And then calculate the sum over sum of log of the ratio of probabilities, right? That is what you will need to calculate. So this will become the new KL loss in some sense. This will become the KL loss. That will be the way to solve it if you want to do a Monte Carlo estimation of the KL loss,
Yeah, yeah.
right? Okay, that is about that. And then we also so we've currently taken one sample for the decoder, again to make coding a bit easy. But rather, if you want to do a better approximation, and we said that because, for example, here, right? So we said that. Yeah, the reconstruction determined elbow. So the idea was that we want to we'll use sampling approximation for this. So currently we're using one sample. So ideally what you have to do is you will take this epsilon. What you will do, you will have one such you'll have L, capital L such values per per element in your batch.
Hmm.
So you have many such epsilons, and then you'll have to add the right mean and the variances, etc., properly, so that for a given x, for its particular samples that you generated epsilons, they get added up properly. And then what will end up happening is you will have this decoder of z that gives you output. It will not be just x hat, it will be multiple x hats, right?
Hmm.
Because for each z you will get one x hat. So then you will then use this idea of again the where we did this one, right? So what will happen is, so each of these terms, right, each of these terms is an MSE in itself, right? So you will have
Hmm.
x hat, let's say b comma l, right, minus x b, the true and you
Correct.
predicted
Correct.
that MSE you will take,
Yeah. Yeah.
and you will take a summation over all
Summation over
the
else. Yeah.
right, all the else, right?
Understood.
This
Yeah.
will be your MSE loss. So it will not be just one term, it will be multiple of those, each of them being compared with the true value. That's the way
Yeah.
you will implement this, right?
Hmm.
Okay, that is that. Then what else did I have here? So actually, so this is a very good data set actually. Dsprite data set. Again, you should try to see implement that here. I tried, but there were some RAM issues, so I just didn't go ahead with it. So the idea here is that, I'll give you a basic idea. So what they're doing here is that they have generated again a grayscale sort of an image. The size is, I guess, uh, how much, 64 cross 64, right? So you have these images, and they have 6 latent factors with them. So one which color controls the color, sorry, color is always white, sorry. The shape is being controlled, right? It's either square, ellipse, or a heart. Scale is being controlled, again, a scale of the, I mean, how big the image should be. Orientation, that is tilt and position x and y, right? So the idea here is that they have generated so many samples, like almost what, 7 lakh samples here, 7.3 lakh samples, images from these ground truth independent factors. So the idea here is that if you use a VAE with hidden dimension equal to 6, for example, right? So you should ideally be able to capture all of these factors properly, right? Because the fact that these are independent, point number one, right? So you should be able to, the whole theory of VA, basically we saw that, we should have independent um, uh, hidden dimensions and all of that. The biggest problem was that we don't know what the number of that dimension is, right? But as we know, data set, we should be able to capture this particular images flawlessly. So give it a try and see what issues you're facing, and then try to intuit if you're facing any issues, why that could be, and what possible things you can do to solve those issues, right? So
Yeah.
this is one very good data set to try and see where VAE can fail, even if many of the assumptions that we have taken are actually true for the data set.
Hmm.
And one again, very another simple thing that you can do is try to see for different architectures. Now we have done basically
Yeah.
just simple MLPs, right? So
Hmm.
but as we know, like in images, CNN seem to have done very good jobs. So ideally, replacing all of these linear layers with, let's say, a convolutional layer, so that might be able to help you do a better job at the even for less number of epochs. For example, even in 10 epochs, you might be able to get very good images of 0, 3, and so on, right? That is one thing that you can do. Uh, Again, we had this. We also spoke about four different VAs. One was beta VA. Again, beta VA very simple to implement. So the idea is that the loss function gets scaled with the value beta, the KL part of it. So what you'll end up doing is you have something like beta into KL loss, and this beta could be like a have parameter which you try to tune based on a validation set. right? So this is basically beta VAE. That's it, right? So the idea being that if you train a model with beta VAE versus VAE, what you need to look for is basically are the dimensions basically more independent or not, right? Compared to a normal VA, because beta VA, the idea is that you want to be able to capture disentanglement in the latent space, right? That is would be a main source of comparison for these two sort of models. That is one thing, and we also have conditional VA. Now, for example, let's say you want to do even number generation and odd number generation separately. For example, let's say take all labels also into consideration, but give me generate only even numbers or generate only odd numbers. So, what part of the code would you think that would get affected, and how you would implement it? Any thoughts on that?
Hmm. Okay, just a minute. Then I'll look at the whole code once.
Sure, sure, yeah.
So VAE class will certainly change,
Right.
and I think encoder and decoder can remain same.
Mm-hmm.
But again, like we have to pass that label information, so something has to be changed there also.
Right.
Because decoding dependent on label.
Depend on the label, right? That's
Yeah, yeah.
the. Hmm.
So I think many things will change then.
Yeah, okay. You're right. First of all, what we need is we need access to the labels in the first place. So
Hmm.
as I mentioned here, that this batch basically gives us the image and what actual
Ah,
decision here is. Huh. So
right.
what is you can let's say let's call this, let's say, digit, what digit is, and then we can generate the label to be, let's say, digit mod 2, right? And say,
Correct.
okay, it'll be 0 if it is even, or 1 it'll be 1 if it is odd. Now the idea is, again, we discussed the conditional VA formulation. The idea being that both your encoder and decoder will need to look at the label Y with
Label
it,
information. Hmm.
right? So what will happen here is, so this Y can no longer be ignored. Rather, it'll have to be passed through the VAE model, so that the encoder and decoder can look at it. So the idea is now this forward function will take both the image and the label associated with it, and encoder and decoder will also have to do that, right?
Hmm.
So now what so the way your encoder will change is basically, if you see the encoder also currently took only the image. So now
Yeah.
rather the label also put in it. So
Right.
so so now the question is, okay, how do we give this information to the what do we change in the
Utilize
architecture?
this
So,
information.
huh.
Hmm.
So basically, we can either give this Y as a 0 1 Boolean value, right? So what we can do is we can say, instead of looking at just the image features, I can make this 784, let's say, +1, right? So
I
I'll
see.
pass image also, image label also, right? With Y. So I'll say, okay, concatenate this, right? Something like, again, this is not the right function, but concatenate X and
Right.
Y, whatever I have, and then just pass this Y through it, right? So I would have passed the label information also through the encoder. Same thing with decoder. Now decoder will also take X comma Y, and same
785. Yeah.
use
Hmm.
here. Right? That's the idea. And then when you're sampling, right? So again, as you said, like all of, so the only thing that changes at the end of the day is the encoder decoder sort of architectures, but the idea is the loss function and all
Everything
of,
remains same.
right? So hence what happens is, so the self of x comma y will still give you only the mean
Mean and log. Yeah.
and x hat, right? So all of
Right.
the your MSE loss that remains unaffected, your reconstruction loss remains unaffected, and all of that remains unaffected. What changes is when you do sampling. So now, previously, when we were generating this z, we just took z and moved ahead with it. But now the decoder expects z comma what label you
Hmm.
want, right?
Yeah.
So
Yeah.
then you, okay, let me see even images, and this will be for odd images, and so on.
Right. Right.
That would be the changes you need to do
Hmm.
to make sure your model can handle conditional generation sort of a problem statement, right?
So basically adding one more dimension to the input image itself.
Correct. Yes,
So
exactly.
that like now label information is also there, and
Right.
hopefully the model will be able to
Use
learn
that
to reconstruct this label information also,
also. Yes, yes, correct.
and therefore utilizing the label information, and hence like.
Right. Yeah, that's the idea. Correct.
Hmm.
So then, but then like, so again, people have done a lot of thought process into how to give this, is conditional, sorry, not the label
Label. Hmm.
categories into this, different ML models. So there are, so for example, let's say we currently had just now, we just looked at two possible labels. So if you have like, let's say, n labels, so then you can do like a n dimensional sort of a one hot encoding sort of a
Hmm.
approach. You will increase so many dimensions in your input,
Yeah.
or whatever, right? So that's one approach you can take. The other approach is, for example, people look at having an embedding layer to capture the categories independently, and so on. So we have a lot of different approaches, but yes, the idea being that that information needs to be share given to the encoder and decoder, so as to make so that it makes use of it. That's the idea,
Yeah.
right? And then we have some more complex things, for example, as the info VA, vampire, VQVA. Again, all of these can be done in this framework itself, but the idea being that all of those require some additional understanding of how to make sure your different parts of the training work together and everything. So I'll
Hmm.
leave it for now, but again, we can discuss somewhere down the line, like because info we will
Yeah. Yeah.
require adversarial learning and all of that. So we'll do it later on. Yeah.
Okay. Okay.
Okay. So yeah. So this is about conditional. Sorry, this is about VAs and conditional VAs also in some sense. So any doubts in the coding part of it? Anything else you want to know?
I think it's fine. Just that like I have to play with some parameters, and once I do that, I will be like perfect in whatever is required for this thing.
Right. Right. Yeah, that's
Hmm.
true. Uh, and we just taken train and test. For example, let's say you might want to tune some hyperparameters for that matter, right? Yeah, beta VAE introduces its own hyperparameter of beta.
Hmm.
We
Yeah.
also
Yeah.
have an alien dimension, which is again a hyperparameter in
Hmm.
some sense. So all of this tuning will need to be done through a validation set. So ideally,
Validation. Yeah.
a train valid that you will do, and then try
Yeah.
to look at the
Yeah.
optimal
Yeah.
hyperparameters and so
Hmm.
on. Again, so those are all the usual ML stuff that comes into this generative modeling framework,
Hmm.
and reason being that because we're using neural networks, so neural networks themselves have a lot of complexity in terms of training and finding out the optimal function as such. So that's
Hmm.
the those are some devils that we need to live with.
Yeah. And when we
Right.
are doing training and testing, how are we dividing the data? 80-20, like for example, 70-30.
So currently this MNIST that we have data set being supported by this Torch Vision, I guess that's the Torch Vision data set. So
Hmm.
it has some split in itself. So we haven't done any external from our side. So but again 70 10 sorry 80 10 10 is is something people do, or people do 17,
Okay.
70, 15, 15. These two are generally usual, methods that the people choose to do. Yeah.
Hmm. Right.
Okay. So yeah. So this closes the tutorial part of the things for today. So as you can see, like,
Just hmm,
yeah, go
one
ahead.
question here. So if
Yeah.
we wouldn't have used torch vision, how
Yeah.
much of it would we have to like code for ourselves?
Okay. So let me
And
share
is
this.
there any harm in using torch vision?
Okay. So at least I would say from my side that there's no harm in using. Sorry, you mean PyTorch Lightning or Torch Vision? You mean?
Oh, sorry, I meant lightning. Yeah.
Lightning, huh. So there's no harm in using PyTorch Lightning, at least not that I have found almost anywhere through my experience of almost 2 years of using PyTorch Lightning. The So what becomes an issue, right? For example, let's say if you want to, okay, so what parts of the code will change? For example, let's discuss that, right?
Hmm.
So this mainly this part of the code, right? So now what will happen is you will have to now do this iteration. Basically you'll say, okay, give me image, give me the label, right? In enumerate, no, not enumerate, you can just do yeah, self model dot, let's say, train data loader, right? Because now this function of the model gives me the data loader with to me, right? So I will do that here. And then what I need to do is things like this. I have to set the model in train mode. So I'll say model.train, and then you have done this. So then you have to run this through the model. So say model dot, let's say, X or whatever, right? Oh, sorry, image here, right? Label is not required for us currently, so you can just ignore it, right? And you'll say, okay, what is the output of this model? And then basically say, okay, try to optimize it. So you'll have to go through this optimization, steps also as part of this loop, right? And then this is for one epoch. You will then say, okay, run this for multiple epochs. So for epoch, in number of epochs, right? And then you'll say, okay, optimizer routine, you'll have here. Now this is for the train part. You'll say, okay, do the same thing for test, because I need to know how the data is working for test data, right? So model.test data loader, you will run this, and then you will say run it in the eval mode, because I don't want to train the model on this the test data part, right? Again, you will do the same model of image, right, and something, and then you'll say, okay, log this loss, whatever you have got here, and then continue. So the issue, at least what I feel when I was coding using this sort of a method, was that it's very prone to your it's very prone to simple mistakes in your code, right? Something which you might not even expect to think about, like some very small thing, but that can affect your either the output, or basically your whole result, in some sense, saying that, okay, you ended up using something from the test data in the training procedure, and so on, right? So all of these sort of issues that can happen, that is sort of what you can say, like handled by PyTorch library in itself, right? So that becomes a very useful part, what I have seen till now. But yes, it does come with some challenges. For example, now in GANs, when you want to do this, having this sort of optimization loop is helpful, because you want to control exactly at which part which optimizer should be used, and all of that. If you want to do using PyTorch Lightning, it does become a bit difficult to do that, right? So the idea being that these sort of high level libraries, they help you in some way to iterate faster. For example, if you want to train different models, for each of them, writing through this sort of a code or trying to write a common code which can work for all different possible cases, all of that becomes a coding nightmare in some sense. So at least my personal experience has been that using this sort of upper level libraries helps you navigate these issues properly. That's my experience again.
Okay, all right. Yeah.
Yeah. Okay, so now we'll go through, we'll continue our discussion from last class upon the adversarial learning problem statement, right? So again, bring back to the first, the problem statement that we had at hand was that we wanted to be able to generate samples which look like the samples that we have at hand, right? And we also spoke of a method which said that it, if we have some known distribution, for example, let's say some known variable, so there exists some let's say function called g, which maps this particular known variable into the unknown distribution variables, that is px, let's say some x here, right, which belongs to RD space. Now, since we don't know this function, we can use a function approximator, and we know that neural networks are the best function approximators in some sense. So now the idea is that how do we train this network? Because as we know, neural networks we will have some sort of initial parameters. We need to train it so that it can become more true to the approximation that we want it to become close to. Uh, so we said that we have g of 0 as the initial parameters. So what this means is that I have a function called g superscript 0. So if I pass this z, which is your known random variable, for example, through this g0, it will give me some x0, right? So this has a distribution called as px0, right? Because x0 can be seen as a random variable, because this is random, this is a deterministic function. So I have a distribution called px0 over this random variable. So now the question was, okay, how do we update this g, right? Because we know for a fact that this px0 is not px, right? Is not px, right? So how do we make sure that we can we basically need some method to tell these parameters that, hey, look, what you're doing is not right. Rather, you need to change in some way so that it become more and more closer to this px, right? So the bigger question is, how do we update, right? So the idea that GANs basically use, and again, this is one of the many different intuitions for GANs, by the way. So one approach here, one way of thinking about the approach is that if we have another network, some other network, or basically some other function, which can tell us that whether whatever samples you got from this G, uh, are they like the samples that are coming from the real distribution, that is px, right? So this function as such, basically, if it tells me that, okay, whatever sample you passed, let's say some x I passed to this f, if it's able to tell me that, okay, this is coming from px, okay, or not coming from px, right? So then what I can do is I can use this information that, okay, oh look, whatever samples you gave me, g0, right, this x0 samples that you gave me, they don't look like px at all. So change yourself so that they become more and more closer to px, right? Samples that I have with me right now, right? That's the idea here. So basically, the point being that so if I have a random variable, let's say z, that is passed through a g function, and that gives me some samples, let's say x, okay, I'll call this as xg, okay, and this is passed through a function f, let's say, and then I have the actual data. Let's say I'll call this px. We don't have px, but let's say samples come from px. I'll call it as x, the real whatever, right? So if I'm able to, so if I have a function which can tell me whether the sample came from the generator, sorry, the g function or the real, that is the true data distribution, right? And we call this g function as a generator function because ideally it's taking some random variable and the samples generating the samples of the px distribution, right? Ideally speaking. So then so this function basically is called as a discriminator, because the idea is that it needs to be able to discriminate between these samples, right? So between generated samples versus the real samples, right? So if it is able to do that, right, then what we can do rather is use this information that okay, so it's like saying that G is trying to basically tell a lie to f, that okay, whatever I generated is x. So if f is able to catch that lie, then we say okay, whatever you told was not good enough, you need to update yourself, right? Give me a better life that I can believe or something, right? So that's the idea. So now how do we update? Again, the question remains, how do we update? So then whenever the samples from G are passed through F, right? And if F was able to tell you that these are actually from the discriminator, we use the gradients coming from this for this particular xg for through this function, right? Because this again a neural network, again we'll use a neural network again here. So the idea is whatever this f generated will have the we will have the gradients with respect to this xg also through this of this network f, right? We'll pass the gradients back into g, right? And trying to make sure that once you update the gradient, once you update the vector, update the weights of G, the next time if I pass the same image, ideally what I want is F to be saying, okay, it is not 0, it is tending towards 1, right? It is tending towards being classified as a real sample. That's the idea. So if I've done that successfully, then I can say that, okay, xg, so G is able to generate samples which are similar or equivalent to X, and therefore I can then use this network to generate more samples instead of relying this on this PX. Yes, Sanchit, go ahead.
No, it's clear actually. So no question.
Okay. So basically the idea here is that F, or let me use D now. It's called a discriminator. So D is basically going to give you, so it'll basically be a classification problem for a D, right? Classification problem. And again, as we know, in classification problems, we basically output the probability of belonging to a particular class, right? So what D will be trying to, what D will output is basically the probability of, let's say, X belonging to the true distribution, right? X belonging to the true distribution. So the idea is that we want G to be G to generate such samples that increase the probability of D telling that okay, that particular image actually belongs to the true distribution. That is the idea, right? And this is what the gradient goes into through xg into G and update the parameters of G, right? That's the intuition behind GANs, right? So, so okay. So, what will be the so post training? What will be the output of D for samples from G or PX? So let's say we have
one for both cases.
No. Think about it.
Okay, so D is being given one particular image, and it
At a
has to
time.
tell whether it's coming from a real distribution or from a fake distribution. Correct?
Correct. Yes.
Now, after a lot of training, when XG is very we are able to get a very good XG, which is as good as real,
Right.
and when we pass it through D, the probability would be 1.
Because see, what is D trying to discriminate is trying to tell you, can I understand whether this image was generated or was it real, right?
Okay, so
So,
you are, I see. Okay, so
huh,
is D also changing? Yes.
D also is changing, correct? Yes.
Oh, okay. So then it will give chance probability.
Chance probability, right? Exactly. है
Yeah.
ना? So because now D, it'll see a sample from G. If G is doing as good a job as PX, then D will never know it's coming from G or PX, because
Correct.
D at the end of the day looks at one sample. It will get some one X it will get, and it has to give it a probability of X belonging to whatever this probability, right? So
Yeah.
if he's able to tell, okay, that G it came from G or it came from PX, that means G is not doing a good job, right? So rather, if D is confused, that basically if D ends up giving probability of X to be equal to exactly half, that means it's confused and it doesn't know
Yeah.
that the X belongs to G distribution or PX distribution, and
Right.
that's when we can say that okay, G has done a good job of approximating PX,
Right. Right.
right?
So,
See?
I was
Yeah,
thinking here actually we neither have a good F nor a good D. So neither a good G nor a good D to start off with. We
correct.
only have some samples to train things. So
Yes,
for example, if we somehow have a very good D, which can see an image and tell whether it's real or fake, then
right.
we need not even update D. And in that case, the only purpose of X, all the gradients would be used for updating XG and making it as close as to the real distribution.
Correct.
Assuming
Yes,
that if D is very good, but I can understand that given that we don't have XGs to start off with,
correct.
so D also needs to be updated. Therefore, towards the end, the probability would be chance, not like 1.
Which chance? Correct. Yes,
Yeah, yeah. Understood.
that's exactly, and that actually ties down into this idea of gradient saturation also. So again, there are a couple of points you raised in your monologue, but we'll discuss each of them in detail. So one idea that you mentioned was this the idea that okay, you don't have enough samples in the beginning to train D itself with, right? So let's say
Hmm.
if you have enough samples also, the issue what happens is something called the gradient saturation.
I see.
Now,
Understood.
uh, so if you think about it, the output of D is in some sense bounded, right? It's
Right,
always
right.
between 0 to 1, right?
Yeah,
So
yeah.
what can end up happening is that your gradients which come up to which flow from D to G can be very
Hmm.
small
Yeah,
uh,
yeah.
to either begin with or even later in the training and so on, right? So
Hmm.
people have while this particular approach is the most the initial GAN that was proposed had this approach in it. There have been other approaches where instead of looking at a probability scale, so now right now what D is doing is looking at just a probability, right?
Hmm.
Probability of, let's say, X belonging to the true distribution, right? Now, can I, instead of using the probability as a metric, right, can I use something else altogether? So, for example, people have tried using some sort of a least squares approach. Again, this ties down to your idea last time that you were saying about MSC sort of thing, right? Again, so again, exact formulations will not look at, but the idea
Hmm.
is that um, uh, gradients can get saturated very fast because of the fact that your D itself, the output itself is sort of bounded in some sense. If we can make sure that D can output not just a fixed range, but rather a larger range, or possibly an infinite possible value sort of a function, right? So I will have enough data to train my G with. That's the
Right.
idea.
Hmm.
Okay. So people came out with something called as least LS GAN. So there is a least squares GAN and something like that. And all of these ideas came about. One big idea in this whole thing was something called as Wasserstein GAN. Again, the math behind Wasserstein GAN is again very unusual and very different. But the idea is this, that your D, instead of giving a probability or some whatever, what D does is it gives a score, which is a real number. Okay, so the D will try to do is that it'll try to give a high score for real images, let's say, again quote real, and low score for, let's say, generated images, right? So you'll try to train D in this format, right? And the aim of the generator, right, is to make sure that its images pass this so-called exam, right? Its images gets high score. That's it.
Right. Hmm.
All generator wants to do. Try to make sure that my images get high score, but D will be trying to look for, try to give high score for real, but low score for generator and so on. That's the, point here. So because this score is real number, and which basically means minus infinity to infinity, so you have actually good flow of gradients for generators, and therefore Wasserstein GANs have been shown to have much stable sort of training, training your generators compared to your usual GANs, which rely on probability metric,
Right. Right. Yeah.
right? So this is one intuition about Wasserstein GAN, and huh, and this is the reason why these are called as adversarial networks, right? Adversarial networks, because D and G sort of are adversaries in this nature. That D is trying to, let's say, in this example example here, if you see that it's trying to give high score for the real ones but low score for generated, but G is trying to make sure that D should output high score for its images, right? So
Hmm.
hence they're trying to do something very different from each other, and hence they are called adversarial networks. Adversary being the keyword, right?
Right.
Now, one other point that you raised in your monologue was this, right? That um uh yeah, so correct. So we don't have an optimal D also to begin with, right?
Hmm.
That is a very big point, because if we have an optimal D, then I can keep on passing the generator images through it, and trying to get as much gradients as possible to update my generator, and be the best, right?
Yeah.
So hence what we do in adversarial networks is we try to train these G and D one after the other. So what we do is we say, okay, we initiate G with some, let's say, initial parameters G0. Um, we pass, let's say, a bunch of images through G0. We get some fake or generated images as such, right? So now
Hmm.
I have a set which is, let's say, X G0, I'll call it, and I have my usual X, right? This is a set that I have with me. I will use this to train my D,
Yeah.
right? So D now gets trained to D1, right? Let's say D0 somewhere, and D, so it becomes D1, right? Now, so now once it has become optimal at different, telling out what X G0 images are, right? So now G0 can use the gradients coming out from D1 to update itself, right? Because because D1 is now optimal to tell you whether the images are coming from G0 or true distribution, right? So this serves as a good gradient for G0 to update itself. So G0, so then what you will do, you'll keep this constant. You not update this guy. You will say, okay, pass all my XG0 through this, get me all the gradients and update myself. Update G1, right? So now G0 became G1 through D1. Now what you will do, you'll fix G1 and pass all the images that you get. Let's say XG1 is the set that you have, and again true images that you have. You'll pass this to D2. Update D1 to D2. So because now what has happened is G has changed. So obviously the descriptor that you had previously will not work better. So you will update D1 to D2 saying, okay, now find out whether whether the image came from G1 or the true distribution. Then once you do that, again same idea. So you'll keep this fixed and update G1 to G2 using the gradients from D2 for all the images of G1. So that's the idea. So we do something like a step-by-step training. So we, I mean, by training in some sense, right? So you update G, keeping D constant, right? You will do this once, and then second step will be again you will update D, keeping G constant, right? Now this will be basically one epoch of your training. You will do this for multiple epochs. That's it. That's the way you will end up doing your this one, right? Now again one small aside in terms of implementing this. Basically what will end up happening is you need two optimizers, right? Because previously we use Adam optimizer in just now the code that we saw to update all the parameters at once. But here we don't want to update all the parameters at once, right? G has its own parameters, D has its own parameters, right? So what we'll do, we'll have two optimizers. One optimizer will be for G, one will be for D, and at a given point in time, even within the single epoch also, what will end up doing is you will end up doing, like, let's say using the G optimizer here and using the D optimizer here. That's the way you will implement it. Okay. All right. So this is about this. And then yes, so we have some other variations also. For example, what people do is um, they do like making your running the second one more number of times compared to the first one and so on and so forth. So again, these are some variations that you can do. So here the idea is that you're running one step of each in one epoch. Rather, what you can do is I'll run this step only once in one epoch. I'll run this, let's say 5 times in one epoch, right? So one epoch in the sense one batch set that you get, right? So basically the idea being so in this one file, the idea being that you want to train the discriminator as much as possible. So you want to make sure that the discriminator is as good as possible. And the reason being that if you do that, you will have very good gradients to train your generator, right? Because once you have a very good discriminator, whatever the gradients flow, they'll be very optimal. I mean, they'll have enough information to update your G to a better position, right? So that's one way of that's one intuition of why you would want to do something like update G only once, but you'll update your discriminator multiple times and so on. That's the idea. Okay. So so any doubts till now?
It's clear actually.
Okay. Yeah, so we remember asking this question of inference in VAs. Again, the inference basically we use the encoder model, right? We pass through the X through this encoder, we get the mean and variance, and we use the mean as generally the mean is used as the inferred latent or whatever, right? So but here we don't have anything like that. If you see, so basically the question is, can we find out this, right? Can anybody give me this? The answer is no. So basically, the question we're asking is, let's say if I have an X, right? If I have, let's say, some X with me, can you tell me which Z could have produced this, right? This exactly what P of Z given X sort of constitutes in a English sentence. So that information we don't have in GANs. In general GANs, we don't get this information at all, right? So GANs basically the bigger point in GANs is basically just to make sure that you get good samples of your data, and this basically this actually falls into the idea of likelihood free learning. So you're not trying to model P of X, P of X given Z, all of that, all of this is not there, right? You're using a very simple idea, the idea of function transformation of a random variable. You have a random variable, you want to transform it into some other random variable, you will have a function for that. The problem is we don't know this distribution, so we'll have so we don't know this function. We'll use NNs to approximate this function. That is it. So there is no idea of there's no idea of this posterior, latent posterior, and all of that here. So this is one problem. I mean, in some sense, you can say that because you don't know what Z is optimal for generating this particular X, and there have been solutions to try to solve this also. We'll look at it in possibly the next class. You're almost at the end of the class. Okay, so inference as such in normal GANs, it is not present. You cannot do inference here. So one issue here is that, see, I mean, ideally what you would want to do is you want to invert this G network in some sense, right? Now that is not an easy thing to do. You know, inverting neural networks from this X back to Z is not a simple thing to do. So we'll see one approach where people, try to build an inference network altogether from it, right? And so I'll give you one thing to leave with, right? So let's say
Mhm.
um, I have a generator network, right? It takes in Z. And okay, let's think about the same cats and let's say dogs example, right? So I have all images of all dogs with me. I want to generate more samples of these dogs, right? So let's say this Z is passed into G, and G always produces, let's say, one particular image of a dog. Okay, so one particular image of a dog here, right? In a nice farm, there are birds here and all of that, right? Always, regardless of Z, it produces this always, right? And this is then passed to the discriminator. What will the discriminator tell you? Will it tell 0.5 or will it tell 0? What do you think?
So the question is whether this particular image
Ah,
belongs to the real dataset or the fake dataset. Okay. So now you
ah.
have a discriminator. Is the discriminator trained or it's like just starting off with?
No, trained. This whole trained network you have with you. So you're trained, taking hours of GPUs and training all of this. And finally, what happened is you got an image from the generator, a nice looking dog, and all the good properties. Like if you see this image, you'll feel like it's a real dog and all of that.
Okay.
So for
I
this,
see.
what did the discriminator give you output? Any thoughts?
So it will give me one. It will give me zero actually.
No. We just discussed this, right?
It's trained.
It's trained. So it's completely trained, right? So ideally, post training, if the generator has done a good job, right?
Okay. Hmm.
So D will ideally give me 0.5.
But I was thinking like given that there is only one particular vector and which is being repeated all the time, and on the
Huh,
other hand you have so
okay,
so you have the entire distribution of real images
right,
compared to only one image generated like 1,000 times or whatever.
right.
So like the discriminator can have can learn this particular example and say like the moment I see this I will say like no it's fake.
No. But the point is this. So what has happened is the discriminator at the end gets only one particular image to it, right? So so basically it'll say, so it'll see an image from px, it'll see an image from this g. The px will also have something similar to it, right? Because it's a very good reconstruction of a
I
dog.
see. Okay.
Nah,
Okay.
right. So I have, it's possible that I will have a similar dog in this particular format, and let's say one less bird or whatever, right?
Yeah, yeah.
So now the discriminator cannot tell whether it was generated or not,
Yeah,
right?
yeah.
And at the end, and again, the bigger reason being the discriminator looks at one image at a time. It cannot look at multiple images, right? So so it sees this particular image, and it says d is equal to 0.5 because it's confused. It doesn't know whether it's generated or real, because it looks very like real, right?
Right, right.
So 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 the idea being that, okay, it cannot tell whether it was real or fake. Now
Correct.
this is a problem, as you said, right? Because now what's happening is the g function as such has not done anything to approximate the px distribution at all, right? G
Correct,
has
correct.
not learned px, right? Rather, but it has done one thing very properly, that is fooling d. That's it.
Right, right.
It has fooled d successfully. That is fine. But
Yeah,
has
yeah. Correct.
px? No. That is the here, right? And this is something
Right.
called as mode collapse, and we'll discuss more about why it is called mode collapse and what could the possible
I
solutions
see.
in the next, right?
Yeah, yeah.
Okay. Yeah. So this is where I stop. Any doubts for now?
No, I think it's clear actually.
Okay. Okay, chalo. I'll.
So,
Yeah.
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 So just, yeah, we can end the meeting and then I'll.
Sure. Let me stop the recording. Chalo. We'll meet next Saturday. Yeah.
Yeah, yeah. And one more